Hi, and welcome to this quick review of atom economy and percentage yield. As usual, the idea is that you watch it after you've done some independent study and note-taking, because it's designed to reinforce the work that you've already done. So first of all, atom economy is a way of measuring how many reactant atoms actually end up as useful product in a reaction, expressed as a percentage. The percentage yield, on the other hand, gives a measure of the percentage amount of desired product you actually get when you carry the reaction out, compared to what you were going to expect in theory. So atom economy tells industrial chemists the likely amount of waste products a certain reaction rate gives, and this allows them to choose a reaction with a high atom economy to create a product that they're trying to make. So percentage yield is the efficiency of a chosen reaction in reality. It shows whether a reaction has actually given the amount of desired product we expected it to. So atom economy and percentage yield are actually two different things and need to be considered separately. So there are a number of factors which can affect percentage yield in reality. For example, did the reaction go to completion? Were there any purification processes required which might have caused loss of product? Or maybe the reaction was reversible in the first place. If it was reversible, could it have gone back the other way to a certain extent? So these all need to be taken into account when making the final decision, when choosing a certain reaction process to make your desired product. So economic and environmental considerations using both atom economy and percentage yield will influence final decisions made by chemical companies regarding the sustainability of a chosen chemical process. Because it costs money to scale these things up to industrial scale and commercial levels, an example might be the Haber process we might have come across this at GCSE. All of this would have been considered well before the Haber process for making ammonia was invested in worldwide by chemical companies. So in order to calculate the atom economy, we take the molar mass of our desired product and we divide it by the sum of all the molar masses of all the products. It's worth pointing something out about atom economy before we go any further. All four of these reactions are encountered at some point during an A-level course. They're commonly come across at different stages in the two-year program. They're all addition reactions. And this means that two reactants combine to make only one product. So any time you come across an addition reaction, you'll never have to actually calculate the atom economy, because there are no waste products and all the reactant atoms are converted into desired product molecules. This can also be explained mathematically by stating that the numerator and denominator, or top and bottom numbers in the expression for atom economy, are the same, which means that it ends up as 1 times 100 equals 100%. So here's an exercise for you. An industrial chemist is given a job to choose a method of making CO2 gas from 3 possible routes, all of which use readily available reactants: carbon, methane, and calcium carbonate or limestone. So for each one, they want you to calculate the atom economy and then decide which the chemist should recommend his company explores further. Now you might have spotted which one automatically is the one to choose, but they did ask you to calculate the atom economy for each one. So pause the clip, give these ones a go, and once we resume the clip, we'll take you through them. So obviously reaction A is 100% atom economy because there's only one product, so this is the one the company should investigate. So for reaction B, to work out the atom economy, you have to take the MR of CO2, which is our desired product, and divide it by the total of all the products. Now there's 2 moles of water and there's 1 mole of CO2, as I've highlighted. So what we do is we multiply the MR of H2O by 2 because there's 2 of them. There's 2 moles of it in the product side of the equation. So if we put the numbers in now instead, we get 44.0 over 44.0 plus 2 times 18.0. So that gives us 55% atom economy. So for reaction C, the atom economy is again the MR of CO2. Divide this by the sum of the MR of CO2 and the MR of CaO, 1 mole each, and then times that by 100. So that gives us 44.0 over 44.0 plus 56.1. So that gives us 43.96% atom economy, which we can now place next to reaction C. So if we now go back to our original scenario with 3 reactions, and assume that our chemist has now gone and trialled all 3 reactions and got the data that's in black at the bottom of the screen. To work out the percentage yield, what you have to do this time is take the actual moles of desired product and divide it by the theoretical moles of desired product and multiply that by 100 to get your percentage. So I'm going to take the 2 definitions from the top part of the screen to make some room for the workings. So the first thing to do is convert the data into moles, so you can insert the relevant moles into the equation for percentage yield. The number of moles of carbon dioxide is 0.0795, using moles equals mass over MR, or mass over molar mass. And in the equation there is a 1-to-1 ratio between carbon and carbon dioxide, so you'd expect to get 0.5 moles of carbon dioxide from 0.5 moles of carbon. Obviously we've got quite a lot less of that. So if you divide the actual moles, which is 0.0795, over the expected moles, which is 0.5, multiply that by 100, that gives you 15.9%. So this would now have to be considered against the 100% atom economy. Let's do the other 2. So employing the same equation, moles equals mass over molar mass, we can work out the moles of CO2 obtained as 0.06, the moles of methane that were combusted as 0.188. So in theory we should expect 0.188 moles of CO2, because CO2 to CH4 is equimolar again, which gives us a 31.9% yield, which is slightly better than before. So let's move on now and do reaction C. So why don't you pause the clip, try it yourself on a scrap of paper, and decide which might be the best reaction out of the 3. So, doing the same process again, one more time, we expect 0.125 moles of CO2, but we only get 0.105. So this time we get a much better yield than the other 2, 84%. So it's clear that reaction C has the best overall balance between atom economy and percentage yield. Now we could improve the atom economy. I'd like you to have a think about this. So a hint might be that calcium oxide, also known as quicklime in the building trade, is used in the construction industry to make cement. So if you maybe sold the calcium oxide, it would then no longer be a waste product, and you'd have 100% atom economy, because you'd have 2 desirable products, not 1. So to summarise, atom economy tells us the percentage of reactant atoms converting to useful products. Percentage yield is a measure of the efficiency of a reaction in reality, and it's affected by several factors. Sustainability, which is a combination of environmental impact and economic viability, is important, and waste products can be used or sold to increase atom economy to make an industrial process more effective. So once again, thanks for your time, and until next time, see you soon.